Content-based routing on live queries. Let's dive into the introduction of this project. So, what is a live query? A live query is a registered query that stays active on the live query server and continuously returns results each time there is a change in the database table on the requested fields. Let's define the research problem with a single statement. How to implement a high-performance content-based routing live query system which runs over heterogeneous data sources. Previously, there was no well-defined approach to specify live queries on heterogeneous data sources. Supporting numerous live queries with minimum latency was also a challenging task. Another problem is that there was not much support for complex queries such as joins, aggregations in the existing systems. So the goal is to address these identified issues after having a thorough research. Now, let's elaborate the project's objectives. The first objective of the project was to create a live query engine that is engineered to seamlessly connect with diverse data sources. The next objective is reducing the latency of serving a live query. The next objective is to empower users to perform multiple stateful live queries simultaneously. The final objective is the ability to perform complex operations on live queries. So now, let's discuss the proposed solution. This is the architecture diagram of our live query system. The users can send live queries using a front end which will route the request to the live query engine. Then the request will be registered there. In the live query server, we use SID as the complex event processor. Therefore, SQL queries must be converted into SIDQL for event processing purposes. For each live query request, a new SID application will be generated. Inside the SID application, the updated data from the database will be processed according to the query logic. From the database side first, the initial data will be taken directly by calling a database API. It will just execute the query in the database and get the results as a normal query behaves. To get the upcoming data, we will use a change data capturing component to capture new updates in the database. Debezium is used to capture change data. By using Debezium, we can capture new events and send them to the SID application. New events will be executed inside the SID application and get a new result according to the query logic and pass the new results to the front end using server-sent events. Additionally, a monitoring and management system is used to monitor the latency per live query, memory, and CPU usage of the entire live query system. SID is a lightweight, open-source complex event processing system that can process streams of events and perform complex operations, such as joins and aggregations. It is preferred for its ease of learning, as it has straightforward syntaxes. SID can be extended to execute complex queries in the live query engine, making it suitable for the objectives at hand. Live Query Server incorporates two approaches to maximize system performance: optimized data broadcasting and column filtering. This figure shows the data flow when content-based routing is not adapted to the system. The traditional approach for handling user queries involves dynamically generating SID applications that connect to Kafka streams to receive data from the Debezium engine in response to database changes. However, as the number of live queries increases, this method puts a heavier workload on the network and consumes more resources in the form of threads, resulting in reduced system performance. This figure shows the data flow when content-based routing is adapted to the system. A content-based router filters and routes specific data to relevant SID applications, while a pub/sub broker system creates subscriptions to a limited number of Kafka streams and broadcasts the data to all SID applications. It is recommended to deploy the pub/sub server in the same environment as the live query server deployment. Location-based routing was adapted to optimize network performance. As indicated in this figure, when user requests are coming to the live query server from different regions, the location-based router detects the location of the user request and redirects the request to the closest live query server based on the proximity, assuming low network latency between regions and inter-cloud provider networks. So, the latency of live query instances and the database server remains low. Let's go into the performance test evaluation. To conduct the performance evaluation in a standard manner, the current live query system is separately deployed on separate virtual machines on Microsoft Azure. Reasons for deploying separate components in separate virtual machines are isolating the effects of each component and generating a real-world scenario. We have used a KSQLDB live query system as a reference implementation for the comparison of our live query system. The live query server, the monitoring component, the database, and the load testing tool were separately deployed in 4 Azure VMS. The database will be populated using the data records of the Edgar dataset. The Edgar dataset contains network traffic information. Initially, the database will be populated using 1 million records, and to evaluate the performance, data records will be continuously pushed to the database. Testing is carried out for stream-only, stream plus single collection, and stream plus multiple collection scenarios. The graph indicates a significant improvement in latency when utilizing a live query server with content-based routing compared to KSQLDB. Since KSQLDB highly relies on Kafka infrastructure, handling the workload can be tricky for a higher amount of requests. KSQLDB mainly uses a query-based approach to capture change data, which requires continuous polling of the database leading to higher latency. The live query server has minimized the disk writes to reduce the latency further. This graph indicates a significant latency reduction when redirecting user requests to the closest live query instance. When a user request from Indian region, it is redirected to a live query server located in central India. Less latency is obtained than when redirecting the request to a live query server located in East US. This is the graph of latency results when the live query server was tested with each 100, 1,000, and 3,000 of simultaneous queries. Handling 100 queries resulted in consistent performance with low variance, CPU utilization below 10%, and a throughput of 600 messages per minute. With 1,000 queries, there was some variance in latency. CPU workload increased to 40–50%, and the throughput reached 6,000 messages per minute. However, handling 3,000 queries led to increased latencies compared to the previous scenarios. The CPU utilization was higher at 80–90%, but the server still achieved a higher throughput of 180,000 messages per minute. So let's start the demonstration of the project. First, we are going to demonstrate the behavior of the live query engine for a select query using a network traffic analyzing web application. To start the live query engine, first, we need to start the 0MQ pub subengine. Then we start the Spring Boot app of the live query engine. Since both components are running on the cloud server with no issues, we can start the front end of the web application. So this is the select query that is used in the user request for the live query engine. So let's start the web app. Let's go to the first sample application. Now the SSE request has been sent, and we will see the results in a moment. As you can see now, the results are getting updated with new ones. This happens because right now, we are inserting new data into the database. Now we can check the latency for this request. So the results are in milliseconds. The first one is the average latency per minute, and the second and the third are the 95th and 99th percentiles of the latency for this request. Now we are going to demonstrate the behavior of join queries in the live query engine using an order management web application. In this prototype, there are two tables, the order table and the item table. Item table keeps all the details of the items of the store, and the order table keeps all the details of the order logs. In this web application, it shows all the newly assigned orders including item details along with it. For that, a live join query has been used. So as before, let's start the 0MQ pub sub server and the live query Spring Boot app. Let's start the front end now. This is the join query we are going to execute. Now the order table and item table are getting updated, and the values will be displayed after the query sends new results. Now you can see new values are getting updated. That means the join query is working as expected in the live query engine. In conclusion, live query server demonstrates approximately 3 times better performance compared to KSQLDB's live query system. While the live query server currently supports single joins and queries, it has the potential to be enhanced to support multiple joins within the same query. Additionally, the live query server can be optimized further to improve scalability and ensure fault tolerance. Thank you.